For today's notes, you will need in class 73. This is part 2 of standard 17. Today we're looking at angles that have vertices on the circle. So the first of those angles is called an inscribed angle. That's an angle whose vertex is on a circle and whose sides contain chords of the circle. So as a reminder from our vocabulary yesterday, the vertex is going to be right here at point A. The chords are AC and AB. And then when we continue that out, that forms the inscribed angle, which is angle BAC, or you could call it angle CAB. The arc that's intercepted is the one that ends up being inside that angle. So for this, that would be arc BC or CB. The intercepted arc, like I just said, is the arc that lies in the interior of an inscribed angle, and it has endpoints that are on the sides of the angle itself. There are lots of things that are true about inscribed angles. The most important is this first theorem. All of the others are results of this one thing being true. So if you know this one theorem at the top, you'll be able to figure out all of the others in problems. But all of the others are nice to know information as well. So inscribed angle theorem number 1. If an angle is inscribed in a circle, that's angle B in this picture, then its measure is going to be half the measure of the intercepted arc. So in this picture, that would look like the measure of angle B being half the measure of arc AC. So half the measure of arc AC could be written that way, or we could take the measure of arc AC and we could divide it by 2. Inscribed angle theorem number 2 is related to that idea. In this picture, we have 2 inscribed angles, and both angle B and angle D intercept the same arc AC. So because of that, they're both going to be half of the same number, which means they'll always end up being the same measure themselves. In other words, if those 2 angles are both inscribed and they intercept the same arc, then they'll be congruent. So the measure of angle B is equal to the measure of angle D because they both intercept the same arc, which is arc AC. Inscribed angle theorem number 3 is about what happens if we have an inscribed angle again, but this time it's intersecting both endpoints of a circle's diameter. So that's this dashed line here through the middle. If that's a diameter, then this arc is a semicircle, 180 degrees, and half of 180 is always exactly 90. So that means that those inscribed angles will always be exactly 90 degrees. Half of 180. Inscribed angle theorem number 4 is if we have a 4-sided shape, so a quadrilateral, that is inscribed in a circle, that means all 4 of its angles are inscribed angles. Then what happens in that case is that the opposite angles will always turn out to be supplementary. So in other words, if we're looking at angle A and angle C, they'll add up to be 180 degrees. And then the same thing for angle D and angle B. They'll add up to be 180 degrees as well. And that happens because if we take a look at angle A, the intercepted arc would be this arc right here. If we take a look at its opposite angle, angle C, the intercepted arc would be this one right there, and together those 2 intercepted arcs add up to be 360. Since they're inscribed angles, their sum would be half of then 360, which is where the 180 or the supplementary idea comes from. And then our final piece of information today before we get to some examples If we have a tangent chord angle, that's going to be an angle where a tangent and a chord intersect each other at a point specifically on the circle. And so since that angle is on the circle, it's going to have the same relationship as an inscribed angle, and the angle will be half, again, the measure of the intercepted arc. So in this picture, we've got our tangent down here. We've got our chord right there. So that means that angle 1 is going to be half of this arc, and angle 2 will be half of this arc. So for angle 1, that's a major arc. So the measure of angle 1 will be half the measure of arc BRD, 3 letters because it's a major arc, whereas angle 2 is intercepting a minor arc, so it will be half the measure of arc BD. All right, those are all the facts. Go ahead and flip the page and we will work through some examples together. We actually have 2 full pages of examples for this notes lesson, and these examples are going to involve both information from yesterday, so we're going to be on the lookout for central angles, as well as information today about angles that have a vertex on the circle. There'll also be the opportunity to use lots of old facts from previous standards, so things like vertical angles or triangle sum theorem, maybe even some parallel lines, isosceles triangles, things like that will be on important information as well. All right, with that being said, we have an arc over here, 50 degrees. That's pretty far away from the angles they're asking us to find, but I'm noticing that these chords are congruent. These chords are attached to arcs that are congruent. That is actually a theorem that we haven't covered yet. That will be part of Standard 18, so I'll just give you that fact to get you rolling on this problem. From there, if I backtrack from that arc, I'm going to connect to this angle number 1 at the center of the circle. Angles at the center are equal to their arcs, so that tells me that angle 1 is going to be 50 degrees. For angle number 2, I have a problem if I try to find an arc to use because I can't make it out to the circle to intercept an arc. So that's a clue that I'm going to need to find that angle a different way. So if we think about this angle 1 as being 50, these 2 segments are both radii of the circle, which means they match. So this little triangle that's here inside the circle is going to be an isosceles triangle. I'm going to draw that out to the side real quick so that we can see it a little bit better. 50 degrees up top and then 2 matching sides, and our goal is to find this angle in the corner. When those sides are congruent, we know the angles opposite them are congruent as well. So we did problems like this back in Standard 3, where we would subtract the angle we knew from 180 to find the leftover number of degrees available. And then because the 2 angles left are congruent, we're going to divide that by 2 to split up those degrees evenly. That will give us 130 divided by 2, or 65 degrees for the measure of angle 2. So a little bit of isosceles triangle knowledge to help us out on that one. Moving ahead to part B, I've got a 120 degree central angle that's attached to an arc. So that intercepted arc right there is going to be equal to the angle at the center. And that's helpful because if we go ahead and we look at angle 1 up here at the top, angle 1 intercepts that same arc, but its vertex is not at the center, it's on the circle. So when an angle is on the circle, that angle is equal to half the arc, or the arc divided by 2, which means angle 1 will be 60 degrees. Angle 2 might not look like an angle to you, but it is this large angle, which together with 120 degrees would make a full rotation around the center of that circle. So to find the measure of angle 2, we're just going to subtract this 120 degree central angle from 360. Angle 2 turns out to be 240 degrees. All right, moving on to letter C. I've got a 35-degree angle here on the circle, so I could follow that out. The intercepted arc over here would be twice as big since that vertex is on the circle, so I could fill that in. Or I could use one of my theorems to notice that this inscribed angle intercepts the same arc as this inscribed angle, so they need to be congruent. So you can jump straight to angle 2 being 35, or you can use your 70. 70 divided by 2, since that vertex is on the circle, also confirms that that angle is 35. I'm noticing a 90-degree angle here, kind of inside the circle, but not at the center and not on the circle. So I can't use that to fill in any arcs, but I could use that to fill in 90 degrees for all 4 of these angles in the middle, thanks to some vertical angles and linear pairs from first semester. And then if we look at this little triangle, I think that's enough information to figure out the measure of angle 1. The triangle would add up to be 180, and I can take away the 90 and the 35 then to track down the measure of angle 1. A couple of different ways to figure out angle 3. Angle 1 intercepts this arc over here. Its vertex is on the circle, so if I take 55, its measure, and I double it, I could fill in the arc. And then angle 3 is also inscribed with a vertex on the circle, so that angle will be half of the arc. Or again, because they're both inscribed angles attached to the same arc, that means that they'll be congruent to each other as well. So lots of different ways to fill in those 3 angle measures. Moving to question D, I'm noticing something from the past. We've got these segments marked with these little flags, which means that they're parallel. So if I'm looking at this 33-degree angle, I'm feeling like alternate interior angles theorem helps me fill out angle 2. Alternate interior angles are going to be congruent, so angle 2 will be 33. Now that 33-degree angle also makes its way out to the circle and intercepts this arc right here. So since that angle is on the circle, I would need to double the angle to turn it into the arc. Angle 1 is at the center, but it intercepts that same arc. Since it's at the center, it will just equal the arc. So angle 1 will be 66 degrees. Looking ahead at question E, I'm noticing I have a diameter in this picture. So that means there's probably going to be multiple ways to solve this one. I could watch for those right angles attached to the diameter, or I can remember that that means I've got semicircles available to use as well. So starting with this 30-degree angle, the vertex is on the circle, and it's going to intercept this arc up here at the top. Since that angle is on the circle, I'm going to need to double it to fill in the arc. And then I'm noticing that angle 2 is also inscribed attached to that same arc, so that's going to also be 30 degrees, congruent to the first or half of 60, however you want to think about finding it. Angle 1 is also inscribed, but it's attached to this arc over here, which is empty for the moment. However, these 2 arcs end to end look like they're attached to that diameter, so that means they're a semicircle. So if we subtract 60 from 180, that should help us to fill in that other arc we need. Angle 1 then is going to turn out to be 60 degrees. Since it's on the circle, it's half of that intercepted arc. The other option, like I mentioned, this whole angle is attached to that diameter. So this whole angle is 90. So if you wanted to use this big triangle, you could subtract 30 and 90 from 180 and figure out that angle 1 is 60 degrees that way as well. Letter F has no numbers attached to it, but we've got that same diameter thing happening again, which means that this arc over here is a semicircle equal to 180. Since angle 1 is attached to that and angle 2 is attached to that, they're both half of 180, which is what makes them both 90-degree right angles. Okay, 2 more to go on this page of examples. For letter G, we don't have any diameters, so we're not going to use 180 or semicircles to help us out. If we follow this 48-degree angle out, however, we can get some information about this arc at the bottom. Since that angle is on the circle, we're going to need to multiply that angle by 2. So this arc is going to turn out to be 96 degrees. And then I'm noticing I have a couple angles attached to that arc. Angle 3 is at the center, so that will just equal 96. Angle 2 is on the circle inscribed, so it's going to be congruent to the other inscribed angle attached, or half of 96. So back to 48 degrees for that one. Angle 1 is going to be another angle that causes a problem because I can't make it all the way out to see what arc it intercepts, which means we're going to need to use our triangle skills to help us out again. And just like the last time we got stuck, this is a little isosceles triangle. So if we pull that out to the side to make it a little bit easier to see, angle 3 is 96 degrees. Angle 1 would be across from a congruent side, so it's going to equal this other empty angle. So we can do our same process as before and subtract 96 from 180 and then divide that leftover amount by 2. Let's double check. I think 180 minus 96 is going to be 84. Yep, and then 84 divided by 2 will give us 42 degrees for the measure of angle 1. All right, letter H, a little bit different than the other problems on the page because they're starting us off with arcs. For all the others, we've started off with angles for the most part. So if this arc is 60, I'm going to follow that back to an angle. Angle 2 is attached to that. It's on the circle. So if the arc is 60, I need to divide that by 2 to fill in that angle. I can do the same thing with this 100-degree arc. Follow that all the way back to the circle. That's going to be angle 1. Since that's on the circle, it'll be half of 100, which is 50. Now, I can't use the 100 to help me with this angle because that's inside the circle. So it's not at the center and it's not on the circle, which is going to be problematic for this angle 3 as well. Now, the good news is angle 3 matches this angle. They're vertical. So because I'm dealing with a triangle here, I can just do 180 minus 50 minus 30 to figure out how many degrees are left for that third angle in the triangle. And then that third angle is going to match angle 3 thanks to the vertical angles theorem. So 100 degrees to finish out that last example. All right, go ahead and flip the page and we'll meet you back here for a few more examples. All right, 6 more to go. On this last page, just be careful. If you have a printed version of this, these 2 problems might be flip-flopped. So just double check that when I'm doing the problem that looks like this, like bow tie thing, you're on the problem that looks like this bow tie. They might be flipped. Okay, first problem here. I'm noticing 2 numbers I have available to me. I think I'm going to start with the 66-degree arc, because I'm noticing this angle 1 back here on the circle that's attached to that arc. So if the arc is 66, I can divide that by 2 and I'll have my angle 1 figured out as 33 degrees. I feel like I'm going to go ahead and fill in this angle here because then I'll know angle 2. So I'm seeing a triangle sum opportunity here. If I take 180 and subtract 33 and subtract 78, that should give me the third angle for that triangle. That's going to be 69 degrees. So if that angle is 69 degrees, then that means that angle 2 is 69 degrees as well. To finish this out, angle 3 is a second inscribed angle attached to that 66. So it's going to be congruent to angle 1, or half of 66 if you want to find it that way. Another 33-degree angle. On to question B, or like I said, remember these might be flipped, so back to question A if that's the case. 110 degrees is attached to the center of the circle. So that angle is going to match this arc out here, which gives us x equal to 110 degrees. We also have the ability in this picture to use some semicircles or linear pairs to help us out. So if we look at that straight line or segment through the center, that would be a diameter, which means we could fill this angle in as 70 if we wanted to. That's a linear pair. Or out here along the edge, we would be able to fill in this arc out here as 70 as well. If we're looking at the middle, we have a second straight line through the middle, so we have some vertical angles available to us, which gives us more opportunity for 70s and 110s on the other side of this circle. And then I think angle 2 is on the circle, intercepting a 110 degree arc. So 110 divided by 2 would be 55. And angle 3 is on the circle, intercepting a 110 degree arc. So same thing, half of 110 is 55. And angle 1 on the circle, intercepting a 110 degree arc. So 55 degrees for that one as well. Example C on this page is our first example of that tangent-chord relationship we talked about on the first page of the notes. So if we're looking at angle 1 right here, the intercepted arc for that tangent-chord angle is this 112 degree arc. The vertex is still on the circle, so that means we're able to take that 112 and divide it by 2, just like we have been with all of the other inscribed angles and their intercepted arcs. And that will give us the measure of angle 1 as being 56 degrees. Now, depending on what order you want to go in, you might find this other arc next, or you might find the other angle next. You can do either. For some of you, you were really good at spotting linear pairs earlier in the school year, so you might want to go with angle 2, because 180 minus that 56 degree angle we just found would be a linear pair that you could use to help you find angle 2, 124. Or others of you are really good at noticing opportunities to use 360. So you might want to go for x by doing 360 minus that other arc. So that's a possibility as well. And then depending on the order you fill those in, you might be able to use your answer here, 248. You could divide that by 2 to get to 124 if you wanted to find that angle that way. Or if you had the 124, you could have multiplied it by 2. So kind of two different options for how you fill in those other two pieces of information. For example D, we have one arc out here and one angle on the inside. I don't see any other angles attached to the 42 degree arc, so I'm going to try to use this 48 degree angle. Since that's on the circle, we're going to need to double it to find this intercepted arc. 48 times 2 is 96. And now, if I'm looking at the x, that would just be the rest of the circle. So we can find that by doing 360 minus the 2 arcs we have available. 360 minus 42 that was already there, and then minus the 96 that we came up with. 222 degrees for that x. Angle 1 is at the center of the circle, so when we follow it out, 96 is the intercepted arc. Central angles and intercepted arcs are equal, so 96 degrees for the measure of angle 1. And we're almost there. 2 to go. For this problem, we don't know any angles to start with, but we do have 2 arcs available and only 1 arc missing. Usually when there's only 1 arc missing, the best thing to do is to find it and fill it in. 360 as the total is going to get reduced by the 143 and the 125 they gave us. So there's 92 degrees left for that last arc. Angle 1 is at the center attached to that 92 degree arc, so that will be equal to 92. Angle 2 is on the circle attached to that. So we're going to need to divide 92 by 2 to figure out what that angle is. but both are related to that same 92-degree intercepted arc. And then last, but certainly not least, one that involves a little bit of algebra here, we've got another tangent chord angle with a vertex on the circle equal to 59. This arc is the intercepted arc, 2x plus 34. And so if we think about the relationship between those two things, there's two ways to deal with this problem. We can double the angle to be equal to the arc. That's what we did in example D. We multiplied this angle by 2 to be equal to the arc. Or we could have written that the angle was equal to half of the arc, or the arc divided by 2. That's what we did here. We divided that by 2 to figure out the angle. Most people find this one a little bit easier to solve than the one that has the fraction, but they should both give you the same answer no matter what you do. 2 times 59 is going to be 118. And so then next we would want to subtract 34 from both sides. 118 minus 34 gives us 84, left over equal to 2x. And then we would divide both sides by 2. If you prefer this option, you could either distribute the 2 and then solve from, or not the 2, excuse me, distribute the 1/2 and then solve from there. Or if you want to get rid of the 1/2, you could multiply both sides of the equation by 2 and then it would just turn it into the equation that we already solved. All right, thanks for watching. We will see you back in class.